So last week we started with the properties of definite integral, and we covered a few problems based on the properties of definite integral. So a quick review. The change of the variable as it is x by t or x by p, x by y will not matter. And if the order of the limits of the integral changes, then the integral changes with a minus sign. And next, integral a to b f of x dx will be integral a to c f of x dx plus c to b f of x dx. C can be any point either inside or outside the interval. So this we discussed. We discussed with examples, illustrations. Next, integral 0 to a f of x dx is equal to integral 0 to a f of a minus x dx, and integral a to b f of x dx is equal to integral a to b f of a plus b minus x dx. Then two very, very important integrals. Integral minus a to a f of x dx is twice of integral 0 to a f of x dx if f is even, or is equal to 0 if f of x is odd. And integral 0 to 2a f of x dx is equal to 0 if f of 2a minus x is equal to minus f of x, and twice of 0 to a f of x dx if f of 2a minus x is equal to f of x. So these were, we discussed these, all of them in detail, and we did problems on these. Okay. Now we'll move forward. We did now what we need to discuss is the properties of integrals for periodic functions. So what we discussed today, properties of integrals involving periodic functions. So let's begin. So let f of x plus t be equal to f of x for all x belonging to the domain, all right, of the function. Generally it is R for a periodic function, but let's say even if it's in a domain and it is periodic only up to a certain domain. Now if f of x is x plus t, so where t is the period of the function, the fundamental period, or it can be the multiple of the period also. T is the period of the function. Function f of x. Okay. Then we have these three properties. We discussed 7 properties. Now 8th one. we'll get integral 0 to nt f of x dx is equal to n times integral 0 to t f of x dx for all n belonging to integers or natural numbers more specifically, but it is valid for all integers also. Then integral mt to nt f of x dx is equal to m minus n times integral 0 to t f of x dx for all m comma n belonging to natural numbers. Here it can be integers. Okay, all these three we will look into. Then integral a plus nt to b plus nt f of x dx is equal to integral a to b f of x dx. This periodic, so these properties arise. So let us take, for example, a periodic function. So let's take sin x, periodic function. I will take the positive side. Just a second. Yeah. So let's take up to 4 pi. 4 pi I'm no 8 pi I'm taking. So huge interval. We'll discuss all the three cases. Using graph, it is easy to explain. So let us look at, so we know what is the period of sin x. Anybody? What's the period of sin x?
Sir, 2 pi.
Yes. So period of sin x is 2 pi. Now when we say, when we are integrating over its period from 0 to 2 pi, let us say. So 0 to 2 pi is this length. All right, marked in red. So this is 0 to 2 pi. So we are integrating this function from 0 to 2 pi. Now, if I do it, if I take n equal to 3, if I take n equal to 3, that means 0 to 6 pi. So let us take this example. So integral 0 to 6 pi sin x dx will be equal to integral 0 to 2 pi Sin x dx multiplied by 3. Multiplied by 3. So you see here, this is one period, and because the function repeats itself and definite integral is algebraic sum of the areas, so we add this. Now, because of the repetition, graph repeats itself. So graph repeats itself. So it is again summation of areas. So you can do 3 times the area within the period. So this is valid. And of course, proof also, it's easy. It is not so difficult. You can do by substitutions. It's not a difficult. We will not get into the proofs right now. Now, suppose I do from 4 pi to 6 pi, or 4 pi to 8 pi, or 2 pi to, this is the first example. Second example, let's take the second example. Let us take 2 pi to 6 pi sin x dx. So this is 1 times 2 pi. 2 pi is the period, and this is 3 times 2 pi. So answer should be 3, okay, minus 1 times integral 0 to 2 pi. Okay, so it will be twice of integral 0 to 2 pi sin x dx. So here you can see 0 to 6 pi. So this in other words, see, we can write this way also. I will write this as integral 2 pi to 0, okay, sin x dx plus integral 0 to 6 pi sin x dx, correct? Why? Because I can use any point within or outside. So this the second integral I'll write first now, 0 to 6 pi sin x dx. Now I'll interchange the limits. When I interchange the limits, I'll get minus 0 to 2 pi sin x dx. Correct? This from the previous result is 3 times integral 0 to 2 pi sin x dx. And this is integral 0 to 2 pi sin x dx, which is again our valid answer. Okay. Geometrically, it is very, very simple. From 0 to 6 pi is this total shaded area. Now we want from 2 pi to 6 pi. That means this area has to be eliminated. That's all. So now only this shaded area. So that is same as how many period lengths? 1. This is 1 period length. This is 2 period length. So it automatically becomes 2 times integral 0 to 2 pi. Got it? So just by period lengths, we can identify how much will be, because go to the fundamental period 0 to 2 pi, whatever is that area, that will be valid for all other periodic areas, all these shaded areas within those periods. Now the last one is integral a plus nt to b plus nt, is integral a to b f of x dx. So example for this, let's stick to sin x example only. I will take integral pi by 6 to pi by 2 sine x dx. Now, this should be equal to, I add, 2 pi to this. Or I add even 4 pi to this, or 6 pi to this. It will be valid. Meaning to the limits, I am adding the period. Let us look at the figure now. So let's look how this is. Okay. So from pi by 6 to pi by 2, this is pi by 2. So 1/3 of this is pi by 6. So let us say it is somewhere here, half, exactly half. So yeah. So pi by 6 to pi by 2. So this portion is the integral value. This shaded portion, the area under the curve will be the integral value. Now, the same will be valid because the graphs are repeating itself because of periodic function. So exactly the same will be valid if you add 2 pi to it. All right, no matter where you go, just add. The graphs are repeating itself, so the values of this areas will be the same. Okay, this will be the same. So 2 pi plus pi by 6, this point is 2 pi plus pi by 6, which is 13 pi by 6. Now this point is 4 pi plus pi by 6, which is 25 pi by 6. And this point is 6 pi plus pi by 6, which is 37 pi upon 6. So from pi by 6 to pi by 2 integral is same as integral 13 pi by 6 to 5 pi by 2, which is the same as integral 25 pi by 6 to 9 pi by 2, which is same as integral 37 pi by 6 to 13 pi by 2. So that is what is this property. Okay. So these are the three properties. Now let's do some examples on this. All right. The first example, integral, evaluate this integral, integral 0 to 100 pi under root of 1 plus cos 2x dx. Yeah, please solve. Please give me an answer. I'll give you 3 minutes time. Waiting for your answer. 1.5 minutes.
Sir, 400.
No.
Sir, root 2.
Root 2. Answer? No. Check.
The 100 root 2.
Pardon?
100 root 2.
Close. But not correct.
200 root 2.
Yes, correct. Correct. Correct answer. Okay. Look at the solution. Look at the solution here. Now, this is by trigonometric simplification, you know, the submultiple angles. This is nothing but 2 cos square x. 1 plus cos 2x is 2 cos square x, because cos 2x is 2 cos square x minus 1. So now this integral 0 to 100 pi under root of 1 plus cos 2x dx is integral 0 to 100 pi under root of 2 cos square x dx. Now, the mistake students make here is they will write this as integral 0 to 100 pi under root 2 cos x. Here is the big mistake. The minute you write it as cos x, you are saying that the cos x values can take negative values also. Cos x can take negative values. So this integrand can be negative, but our original integrand is not a negative, it is a positive. It's a non-negative quantity because there is no negative sign associated with the under root. This is already a positive under root. So here, very important, you have to take a modulus. It is root 2 modulus of cos x. That is the catch for this problem. Now, what is the period of mod x? Period of, what is the period of this function? Answer? Anyone?
5.
Hmm? The period of this function is pi. The period of cos mod cos x is pi because say this is cos x. This is the graph of cos x. Now next I will draw modulus of cos x. You see how it is, modulus of cos x. So the period is pi. After every pi, if it was cos x, the period was 2 pi. The repetition is after every 2 pi value. But if it is cos x, mod cos x, the repetition is after every pi, because negative side, the graph portion of the graph on the negative side has gone to positive. So period of modulus of cos x is pi. And now you see from integral 0 to pi, this portion of the graph is repeating. This area is symmetric to this area about pi by 2. So this will be same as, so first of all, because this is periodic with period pi, we can write this as 100 times integral 0 to pi root 2 mod cos x. So now within 0 to pi, modulus of cos x, okay, I'll not change it again, is this. Now further 100 root 2 into, now mod cos x, you can write this function. This we have used this property, integral 0 to nt f of x dx for a periodic function is n times integral 0 to t. That's what we have done. Now f of pi minus x for this modulus of cos x, this will be mod of minus cos x, which is modulus of cos x, same as modulus of cos x, which is f of x. So therefore use integral 0 to 2a f of x dx is twice of integral 0 to a f of x dx when f of 2a minus x is equal to f of x. So this is what I'm using here now. So I will write this as 2 times integral 0 to pi by 2, because 2a is pi, so a will be pi by 2. So twice of 0 to pi by 2 modulus of cos x dx. So this is 200 root 2 times integral 0 to pi by 2 cos x dx, because in this interval 0 to pi by 2 cos x is positive. So modulus of cos x will be cos x. If at 0 to pi we remove root 2 mod, if you remove the mod, we cannot, because cos x changes sign between pi by 2 to pi. Pi by 2 to pi, it is negative. So we should remember that. So now this is simple. This is sin x is the integral from 0 to pi by 2. Apply the limits. So you get sin pi by 2 minus sin 0. So you get 200 root 2. This is the answer. So we used the periodicity, and of course I would say you can do it much fast. You do it 0 to graphically. Again, I'm just going graphically without all these steps. Last time I told you that for this portion, so okay, let us see the graph of sin x. I said one portion from pi by 2 to pi, or from 0 to pi by 2, the integral value is 1. So this from pi by 2 to pi, the integral value will also be 1. So similarly for cos x, it so happens that this portion that you are seeing here from 0 to pi by 2, this integral will also be 1, because it is just you obtain cos x graph by shifting the graph by leftwards by pi by 2. That's all. So this portion will be 1. So if this portion is 1 and this portion is 1, so integral 0 to pi is 2 mod cos x. The value is 2. So if you remember that 2, So from here, 100 into root 2 times 2 will straight away give you 200 root 2. So you can avoid all these steps if you have a graphical understanding. After this point, straight away you can write 200 root 2. All right. So need to practice this. Now next, evaluate this integral. Integral 0 to 1000 e power x minus the integral part of x. Please answer this. Let's see. Time starts now. Who will answer fast? I'll see. I've got one answer so far. Let's see. Okay, we'll stop. Please listen at the solution. So we know what is x minus the integral part of x. It is fractional part of x. And we know how the graph of fractional part of x looks. What is the period of fractional part of x? One. Period of the fractional part of x is 1. So the graph keeps repeating itself like this. This is 1, 0, or minus 1. This is 1, 2, 3, 4, 5. So fractional part of x It's a fraction, right? Fraction varies from 0 to a number just before the integer. So has a period equal to 1. So now, so I is integral 0 to 1000 e power fractional part of x, which is same as 1000 times integral 0 to 1 e power fractional part of x. Now, in this particular interval, from 0 to 1, fractional part of x is equal to x, because between 0 and 1, this step x or integral part of x is 0. So we can see here between 0 and 1, the curve will be, along this line y equal to x. So y equal to x will be the equation of this line. So that means fractional part of x is equal to x. So we can replace fractional part by x. So now when we integrate e power x, it is e power x. Now you integrate, apply the limits from 0 to 1. So we get e power 1 minus e power 0. E power 0 is 1. So we get 1000 times e minus 1. This is the answer. This is the answer. Okay. Got it? Please take down. Thousand times e minus 1. Okay, next. Extension. Integral minus pi to 199 pi of under root 1 minus cos 2x upon 2 dx. Please find this out. Good. Many answers? Yes. Good. So 1 minus cos 2x upon 2 is 2 sine square x upon 2, which is sine square x. So the under root of it is under root of sine square x. Again, here we have to take this as modulus of sine x. So therefore, integral is same as minus pi to 199 pi modulus of sine x. What is the period of mod sine x? Pi. So period of mod sine x is pi. So this is mt to nd. So m is -1, n is 199. So this is 199 minus of -1 times integral 0 to pi mod sine x dx. Okay. This is 200 times this integral, and from 0 to pi, sine x is positive. Now sine x, the curve, let's go up, the sine x curve. From 0 to pi, it is this full half wave. So from 0 to pi by 2, the integral value is 1. So pi by 2 to pi, it's 1. So the integral value without evaluating, you can directly say it is 2. So we get 400. Okay. All right. Now the same problem, I'll change the limits. You just see whether you will be able to solve it. I'll see who will do it fast without a mistake. Integral 0 to 16 pi by 3, the same problem, 1 minus cos 2x by 2 under root. Got one answer, but it's not correct. Second answer also. Two more answers I've got, which are not right. Rethink. Another half a minute. Good. One correct answer. Very good. Now look at the solution. See, when we gave this result, periodicity, we made one important point that this n has to be an integer or a natural number. It cannot be a fraction. It cannot be a fraction. What happens if it is a fraction? Let's see this. Okay, this is the graph. Now, what is 16 pi by 3? Let us first check. This 16 pi upon 3 is nothing but 5 pi plus pi by 3. So where is 5 pi? 5 pi is here. Of course, this is sin x, this not mod sin x. Mod sin x graph, negatives will go to positive, but I'll just hand draw this. Okay. Sorry, it's a approximate. Anyway, so 5 pi plus pi by 3 is somewhere here. This is 16 pi by 3. 5 pi plus pi by 3. Now, we cannot do it only when it is for over a full period. That whole graph can be repeated. You cannot just do this for, you cannot just write this as 16 pi by 3 times. So many of you made this mistake. Integral 0 to 16 pi by 3. This is mod sin x. What you have done is 16 by 3 into integral 0 to pi mod sin x dx. This is what you have written. This step is wrong. Okay. The correct step is this. Integral 0 to 5 pi plus pi by 3 modulus of sin x dx. This will be 0 to 5 pi mod sin x dx plus integral 5 pi to 5 pi plus pi by 3 mod sin x dx. Now, on this we can apply that periodicity formula. 0 to 5 integral 0 to pi mod sin x dx, because period of mod sin x is pi. Now this here, it is a a plus nt to b plus nt. So it will be integral a to b. So 5 pi is your nt, t is pi, and this is n is 5. So this is same as, so this portion, if you look at the graph, this portion will be same as this portion here. Say pi by 3 so from 0 to pi by 3. This portion of the graph will be same as this portion of the graph. So we will write this as 0 to pi by 3 modulus of sin x dx. Okay. This is the property we have used. Of course, it's not just a property, it's a common sense things that we deal with the periodic functions. Now this is 5 times modulus of sine x from 0 to pi. So from 0 to pi, modulus of sine x will be sine x. The whole integral value is 2. All right. Here it will not be 2. You will have to evaluate it. Modulus of sine x will be sine x in this interval. All right. In 0 to pi, it will be sine x only. So derivative is integral is minus cos x from 0 to pi by 3, which is 10 minus of taking outside cos pi by 3 minus cos 0. So 10 minus half minus 1. So you get this as minus half into minus sign will be plus half. So it is 10.5 or 21 upon 2. This is the correct answer. This is the correct answer. Okay. So these are some very simple but basic problems you can see, and many problems in gate level paper you will see on integrals, they will be quite simple, little common sense you will have to use. Next, an important topic. Before we go further to limits of a sum, I will give Walli's formula, which is, it is a reduction formula. We know what are reduction integrals. Now this is very useful in dealing with sine and cos functions. So Walli's formula states that if I is integral of 0 to pi by 2 sine raised to the power m, sine x raised to the power of m, and cos x raised to the power n. Okay. Now this is of course valid for m and n being integers. If they're not integers, this will not be valid at all. Okay. Now 0 to pi by 2 sine power mx cos power nx dx. This will be equal to m minus 1 times m minus 3 times m minus 5 goes on till 2 or 1. Either the sequence should end at 2 or it should end at 1. If m is even, it will end at 1. If m is odd, it will end at 2. Multiplied by, do the same thing for n minus 1 times n minus 3 times n minus 5 times 2 or 1 upon, now take this sum of m plus n, sum of the two, m plus n times m plus n minus 2 times m plus n minus 4 ending at either 2 or 1. Okay. What are we doing? Just look at this. Before I explain further, multiplied by p. P is a number. Now, where p is equal to pi by 2 if both m and n are even natural numbers. And it is equal to 1 for all other cases. Okay. That means if any one of them is odd or both of them are odd, then p-value will be 1. So what we have done is we have taken m. Now reduce m by 1 digit. All right. So if m is say 9, you make it 8. And then after that, write in a decreasing order, write alternate numbers starting from m minus 1. So m minus 1, m minus 3, m minus 5, and end the sequence either in 2 or 1. This is a product. Similarly, we do for n. However, for the denominator, we don't reduce either m or n. We just add them, m plus n, and then keep taking the alternate numbers. And if p is even, sorry, p will be pi by 2 if both m and n are even. Now, if n or m is are equal to 0, then that is treated as even. Okay. Note, if m or n equal to 0, then treat along with even numbers. So let's take some examples. It will be easy. Now, we get this type of an integral while doing evaluating volumes, and that time it is useful to know this integral. And sometimes in GATE, an integral has been given directly like this. Of course, you can take a substitution and do it, but if you know the Walli's formula directly, you can solve. I have given one such example in the practice assignment, which I have released today. So you can see that. So now let us take an example. Examples on this. Yeah. Integral 0 to pi by 2 sine to the power 6x cos to the power 4x. So so this is I'll explain using Walli's formula. We are not proving this. We can prove this by, again, there's a proof using gamma functions. Will not get involved into it, but directly using this formula is very useful from reduction formula of integrals. So take m is 6. So 6 minus 1 is 5. Then you get 5. Alternate number after 5 decreasing is 3. Then 1. And here. Then 4. N is 4. So you get 3 and then alternate number 1 divided by 6 plus 4 is 10. 10. Alternate number, keep reducing and writing and keep writing the alternate numbers. 10, 8, 6, 4, 2. That's it. You cannot write 0. It will end in 2. Multiplied by, now because both are even, this will be pi by 2. So now let us simplify this one. So 3, cancels this twice, and then there is no other factor of 3 in the denominator. Then 5 strikes 10 and gives 2. So we are left with 3 pi upon 8 into 864 into 2, 128. 1 second. Yeah. 8 into 864, 128, 256, and 512. All right, 3 pi upon 512 is the answer. Okay, so this is the Walli's formula, and it will give you the perfect answer. You don't have to worry on that. Let's do another example. Integral 0 to pi by 2 cos power 8x. Please give the answer. Now m is 0, so that should be treated like an even number. So I will be, for m, there is no factor, so you just leave it as 1. For n, it starts with 8 minus 1, 7, 5, 3, 1. Divided by m plus n is 8, 8, 6, 4, 2. Multiplied by pi upon 2. So again, we have, 3 strike 6, giving 2. Then we have 7 into 5, 35 pi upon 8 into 8, 64, 2's 128, 2's 256. So 35 pi upon 256. Okay. One more. For those of you who finished copying, please attempt this. Integral 0 to pi by 2 sine power 7x into cos x dx. Please give an answer to this. Good. Good. Yes. Answer is 1 upon 8. Now, both of the powers are odd. So P value will be 1. P value will not be pi by 2. P value will be 1. So let's write this using Walli's formula. This will be 6 into 4 into 2. Now cos x is power is 1. You cannot reduce it and make it 0. So you have to leave it at 1 there. 7 plus 1, 8. So 8 into 6 into 4 into 2. Multiplied by 1. P value will be 1 because unless both are even, it is 1. When both are even, it is pi by 2. Otherwise, it is 1. So 6, 4, 2 cancels. You get 1 by 8. And this is straight away, you can observe it directly. If I write sin x as t, then cos x dx becomes dt. This becomes t power 7. So it becomes t power 7 dt will be t power 8 by 8. So that will be sine power 8 x by 8, and substitute the limit 0 to pi by 2. You will get 1 by 8 minus 0, 1 by 8. Okay. So I hope you get it. One more we will do, and we'll stop on this. We'll go further. This integral 0 to pi by 2 sine power 5x cos power 7x dx. Good, good. Three correct answers. Others? Good. All right. Good. So this is 5 minus 1, 4 into 2, leave it there. And then this is 7 minus 1, 6 into 4 into 2. 5 plus 7 is 12. Keep reducing. 10, 8, 6, 4, 2. Multiplied by 1 because both of them are odd. The powers are odd. So 642 cancels, 642 cancels. 4 times 2 is 8. That cancels the 8 in the denominator. So we are left with 1 upon 120. Okay. So this was about using Walli's formula in definite integrals. And it is useful to solve problems, and instead of going through substitution and the long process, we directly use Walli's formula and get the result. Now, very important. Now, summation of series by definite integrals. Summation of an infinite series So summation of an infinite series using a definite integral. Now, how do it? First, we should understand the going back to the basics of what a definite integral is. Now let's consider a function. say y equal to f of x from A to B. Now, let us divide this interval into n equal parts. So in this portion here, now n equal parts will be, say, so what will be the interval width h? If h is the interval width, h will be b minus a upon n. Okay, that will be the value of h. So this will be a plus h. This will be a plus 2h, the second one. All right. Third one will be a plus 3h, and so on. And this one will be a plus n minus 1 times h. Now, how do we evaluate definite integrals? So we know, as I explained earlier, as h tends to 0 or as n tends to infinity, we do summation of all these rectangular areas. We assume that this interval width is so small that we can treat these as rectangles. Okay. Now we can take the lower sum or upper sum. So area under the curve will be equal to limit h tending to 0. Now either it is h times f of a plus h times f of a plus h plus h times f of a plus 2h plus h times f of a plus n minus 1 times h. Or this is same as, or this is also equal to h times f of a plus h. What am I doing here? See, what is this first term? H times f of a. H is this width. F of a is this height. Okay. So h times f of a gives me this shaded portion area of the rectangle. I can get the same rectangle like this. So if this is a, this is h times, sorry, yeah. So I'm taking the lower one, f of a, h times f of a. So we are choosing the left side of the subinterval as the height of the rectangle. We can get the same by using, instead of this area, we can use this area, the right side of the subinterval. When you use the right end of the subinterval, you get h plus f of a plus h plus h times f of a plus 2h plus h times f of a plus 3h h times f of a plus nh. Okay, this is area under the curve as limit h tends to 0 or n tends to infinity. It's one and the same. This is the now I will write this like this. You see here, I will write this as sigma Now h, first I'll write in terms of h, then I will change it. Now h remains constant here, but anyway, I'll write this as h times f of a plus rh. Okay. R varies from, in this case, the first case, 0 to n minus 1. N terms basically. Limit h tending to 0 or limit h tending to 0, the second part, the second equation, sigma r equal to 1 to n h times f of a plus rh. Okay. What is h? B minus a. Now, write h as b minus a upon n. Okay. If we do this, we get the integral value as, what is that integral? A to b f of x dx is equal to, just see here, see from first principles, we derived it very, very simply. I'm now h tending to 0 means n tending to infinity. So now I get an infinite series. Sigma r equal to 0 to n minus 1, b minus a upon n times f of a plus r times b minus a upon n. Okay. Or it is same as limit n tends to infinity, r equal to 1 to n, instead of 0 to n minus 1. Either it is 0 to n minus 1 or 1 to n. Remember that. B minus a f of a plus r times h. So b minus a upon n. You can derive this in 2 steps basically. It is not, even if you don't remember, you can derive it in 2 steps. Now a special case. So this is your integral. So this is the formula. If you have a infinite series as on the right hand side, that you can replace it by integral a to b f of x dx, provided you get it in this pattern. Now we'll see the pattern. This one is a little difficult, but now consider a simpler case. Consider a equal to 0 and b equal to 1. Okay. So what happens to all this? So you get limit n tending to infinity, sigma r equal to 0 to n minus 1. Now you get b minus a is 1 upon n, f of b minus a is 1. So you get r upon n, f of a is 0 and b minus 1 is b minus a is 1. So 1 by n f of r by n. This is very, very simple. If 1 by n f of r upon n. Now this is integral 0 to 1 f of x dx. Very simple. If we get an infinite series in this form, then it is same as integral 0 to 1 f of x dx. So in sequences and series, some of the infinite series, we evaluate those infinite series in this way. Okay. So let's take examples now. So this is the second result and more useful result than the first one. The first one, we don't often do it this way. It is difficult to deduce many times, but this one is much easier. Let's take examples. Okay, evaluate. Limit n tends to infinity. 1 upon under root 2n minus 1 square plus 1 upon under root 4n minus 2 square plus 1 upon under root 6n minus 3 square, so on. The last term is 1 upon n. So how do we evaluate a series like this? This is an infinite series. Immediately when you see, it is difficult to conclude anything. But we have to look into the sigma terms. First of all, let us identify what is R. R has to vary from say 0 to n minus 1. So let us identify R. Either it has to vary from 0 to n minus 1 or 1 to n. That is also valid, as we saw. So let us write limit n tends to infinity. This is 2 into n. This is 4 into n. This is 6 into n. And here it is 1, 2, 3. So R, here you can take 1. Here you can take 2. Here you can take 3. So if you observe very carefully in this pattern, this is 2n times R minus R square. R changes from 1, 2, 3 up to n. So you can see 2n minus 1 square when R equal to 1. The next term is 4n minus 2 square. The next term is 6n minus 3 square, so on. So it's the matter of identifying what is R. Once you write that, then write this as sigma R equal to, 1 to n. Either it is 0 to n minus 1 or 1 to n. Now, we have to get a function in this form. 1 by n and f of R by n. So now you observe this. Can we do this here? Then we'll look at this. Can we do this? 1 by n I need. So I don't have it readily. What I'll do, I'll multiply and divide by n. So sigma R equal to 1 to n. I'll write 1 by n because I need it, and I divide it within the denominator here. Multiply and divide by n in the denominator. That n I take inside, it becomes n square. So division by n square gives me 2rn by n square is 2r upon n minus r upon n the whole square. Now this is in the form 1 by n f of r by n from this integral here. So what should you do? This 1 by n you have to replace with dx. F of r by n you have to replace with f of x. So 1 by n becomes dx, and this limit n tends to infinity, this sigma sign becomes the integral. Okay, so this portion, the sigma with the limit, becomes the integral 0 to 1. Now f of r by n becomes f of x. So I get 1 upon under root 2x minus x square. and 1 by n becomes dx. So I get integral 0 to 1 dx upon under root 2 minus x square, 2x minus x square. So this is the integral. Now we can simplify it further in standard forms. This is x minus 1 whole square with a minus sign. Add and subtract 1. You will get 1 minus of x minus 1 the whole square. You see here? This is x square minus 2x plus 1. When you open the bracket, 1 and minus 1 cancels. Minus 2x becomes plus 2x and x square becomes minus x square. So this expression and this expression are the same. And this is nothing but sine inverse of x minus 1, this integral. So based on the standard result that we have discussed, dx by under root of 1 minus x square is sine inverse x. So x is replaced by a linear x minus 1. So instead of sine inverse x, you get sine inverse x minus 1. So we get sine inverse of 0 minus sine inverse of minus 1, applying the upper and the lower limits. Sine inverse 0 is 0. Sine inverse of minus 1 is minus pi upon 2. So we get the value of this infinite series as pi by 2. We get this value of this infinite series as pi by 2. Okay, very useful. Very useful. So remember, again, here, when you get it in this form, replace r by n by x, r upon n by x. All right. This is the first one. 1 upon n by dx. 1 upon n is the interval width. All right, it's dx. B minus a upon n, it is the interval. It's dx. And this summation sigma r equal to 1 to n or 0 to n minus 1, limit n tends to infinity by integral 0 to 1. Okay. So by doing this, we get the result. One more problem on this type. Find the sum of this series as n tends to infinity. The series is under root n upon 3 plus 4 under root n the whole square plus under root n upon under root 2 times 3 under root 2 plus 4 root n the whole square three under root 3 plus 4 root n the whole square Hmm. 1 upon 49n, the last solution. Okay, I'll do the solution, but you be with me. You tell me what is R in this whole sequence. What is R?
So the quantity under root in the denominator.
Yes. So this expression, this is R. All right. Here it is 1 times 1. This is root 2 times of 3 under root 2, then of course whole square here. Other things are not changing. So this has to be r. So the rth term root n by under root r by 3 under root r plus 4 under root n. This is the rth term. Okay. Now what do we do? Write limit n tends to infinity sigma r equal to 1 to n under root n by under root r times 3 under root r plus 4 under root n whole square. Okay. Now I have to get 1 by r upon n, expressions of r upon n, and 1 by n I have to get separately. So r upon n I'll get here. I will take this under root n outside the bracket. This is a matter of just manipulating. Manipulations has to be right. So 1 upon under root of r upon n times 3 under root of r upon n plus 4 the whole square. What have I done? I have taken under root n outside. So I'll have to divide this term by under root n. So that under root n whole square becomes 1 by n. So now I have got 1 by n f of r by n, this form. So because it is 1 by n f of r by n, it is integral. This expression is replaced by integral 0 to 1. 1 by n is replaced by dx, and all r by n is replaced by x. Okay. So now evaluating this integral, put 3 root x plus 4 as t. This implies 3 by what is derivative of root x? 1 upon 2 under root x dx is dt. So what do you get? Dx upon root x is 2 upon 3 dt. And what about the limits? What happens when x is 0, t is 4. When x is 1, t is 7. And of course, it's a continuous interval because x is varying from 0 to 1, and this is a continuous function. So it is valid. T is a continuous substitution. So this substitution is valid. So therefore, this integral I becomes integral 4 to 7, 2 upon 3 dt by t square. Okay. So 2 upon 3 into minus 1 upon t from 4 to 7. So take the minus sign out, minus 2 by 3, and substitute. So 1 by t is there. So 1 by 7 minus 1 by 4. So minus 2 upon 3 times. This is 4 into minus 7 is minus 3 by 7 4's 28. So minus into minus is plus. 3 cancels. 2 upon 28, 1 upon 40. This is the answer. Okay. Summation of series as and definite integral. So again, this is another infinite series which we could convert to this form, and use an integral. Clear? All right. Let's go to another question of this form. Example 3. Evaluate limit n tends to infinity n factorial to the power of 1 upon n by n. Okay, limit n tends to infinity n factorial n factorial raised to the power 1 upon n upon n. Now in this particular case, there is no summation. How to do then? Any suggestions? Directly, this problem is a very difficult problem. There is no standard way to do it. So as it is, it appears to be a limit problem, but it does not meet any of the standard forms that we have discussed in the past. So how to do this problem? Has any of you come across this? If yes, raise your hands. No. Okay, interesting. All right, look at this. I will write this as, let this be m. M is limit of n tending to infinity. What is n factorial? I'll do this way. I will write this as n factorial upon n raised to the power n to the power 1 upon n. Then I will write this as 1 into 2 into 3 into 4 up to n, that is n factorial. And this n power n will be 1 upon n by 2 upon n by 3 upon n by n upon n whole raised to the power 1 upon n. Now, any idea clicks? Anybody? How to convert this to a sum? It's a product. I have to convert this to a sum.
Sir, applying log.
Yes, very good. Very good. Who was it?
So win my.
Yeah, good. Prasanna also answered that. Good. So applying log. So this implies logarithm of m. Limit n tends to infinity. Log of a power m is m log a, right? So you get 1 by n logarithm to the base e, of course, times this product, logarithm of this product. Okay. So this is limit n tends to infinity 1 upon n times this becomes log 1 upon n plus log 2 upon n plus log 3 upon n log n upon n. Now we have converted this problem to a summation problem. Limit n tends to infinity 1 upon n sigma log r upon n. R ranges from 1 to n. So this is 1 by n f of r by n, r ranging from 1 to n. So this is same as integral sigma becomes integral 0 to 1, as long as it is 1 by n. If it is b minus a by n and a plus r into b minus a by n, that form, then it is integral a to b. But so far we are doing 0 to 1. So 1 upon n becomes dx. Log of r upon n is log x. Now integral of log x is x log x minus x. This we have done it. Okay. This we have done it already from 0 to 1. Now log 0 does not exist. Log 1 exists. So it is 1 into log 1 minus 1. Log 1 is 0. So it doesn't matter. Minus of, this is limit x tending to 0 plus, because function does not exist at 0. So you will have to go to the right limit at 0. So we get minus 1 minus, as x tends to 0, the second term is 0 anyway. We are left with only the first term. We use what? L'Hospital's rule. I have a way to remember this limit, by the way. Okay, anyway, I'll just explain. Log x, differentiate the numerator and the denominator separately. So we get this as limit x tends to 0 plus minus x. So minus 1 plus 0 minus 1. So log m we have got as minus 1. Log m to the base e as minus 1. So m is 1 upon e. Therefore, this limit n tends to infinity, n factorial to the power n upon n is 1 upon e. An important problem. Looks very simple. Okay. Good. Now I wanted to tell a small trick of how can I say what is the value of integral 0 to 1 log x. For that trick, we need to know the graphs of e power x and log x. These are inverse of each other. So let's look at the graphs. Okay, this is the graph of e power x. Now, and let us draw the graph of log x also. Now, this e power x from minus infinity to 0 in this interval here minus infinity to 0, this integral value is 1. You can check it. It is e power x. Integral is e power x. Apply the upper limit. E power 0 is 1. And e power minus infinity becomes 0. So this is 1. Integral minus infinity to 0 e power x is 1. So this particular shaded portion, the value is 1. This area is 1. Okay, this is y equal to e power x graph. Now log x is just a reflection of this graph about the line y equal to x. So this shaded portion will be same as this shaded portion. So integral 0 to 1 log x dx will be same in magnitude, but because this shaded portion comes below the x-axis, it will have a negative sign. Therefore, this value will be minus 1. That's a very logical way to think about it. And when you get integrals like this, you don't have to evaluate. You can just directly substitute the value and get the answer. All right. So this is the trick. All right. So that's it for today. Tomorrow's class, I have already uploaded assignment problems on integrals. Some of them involve improper integrals, and I'll cover that tomorrow. Tomorrow in the first part, in the first 15-20 minutes, I'll cover that. And we'll do a few more problems. And then we complete integrals, and then we'll touch upon areas under curves for simple, two-dimensional curves. That's all. Later, once we do functions of several variables, we will cover integrals with multiple variables. So areas under curves for simple functions, that will with that we will end the calculus for single variable function. So actually I wanted to give a test to you. I wanted to give a test based on differential calculus, but I saw that the number of questions in JEE that comes from integral calculus for a single variable is limited. So I'm sorry, for GATE, it's limited. So we will combine the entire calculus, differential and integral for a single variable, and I'll give you a test. And from next week on, we will do calculus of functions of several variables, or what is called as the multiple variate calculus. All right. Do you have any questions? So tomorrow's class, please come prepared. Come with preparing the previous videos or notes I have uploaded anyway. You go through them, and we'll continue from where we have left today. And tomorrow we will do some number of problems. For first 1 hour or first 45 minutes, we will do problems on integrals, and then we'll move on to areas under curves.